Hello and welcome to part 4 of our 6-part start to finish HEC RAS model with a running wish list in the background. In this part we'll cover flows, so bringing back one of the props from the last part, we're basically taking this impervious perimeter that we've drawn over our terrain data. We've now discarded everything outside of it, and now we're just going to add water to that terrain. So to do that, we'll have to punch some holes in the perimeter, or the top, or the bottom of this thing. I'm not going to go ruin my cookie cutter for this, but if you use your imagination, that perforation will now let water in or out of our model. And that way we can see how it flows over the terrain features that are inside of this perimeter. So changing up the background a bit here, in our demo model, which you can follow along with here if you'd like, we're testing out the berm around Disneyland to see if it will hold water. So in the previous parts, we set up the project file in part 1, we pulled terrain data into RAS Mapper in part 2, and we set up the geometry in part 3. So now let's have a look at that process so far in the schematic view. I've changed the look of this one just a bit since I'm going to start putting everything into dark mode when we get into the 2025 version, but it's still the same concept that you can find in this PDF file of the workshop guide. And that's available in the links below. But now we've got a PRJ file, that's the project file. We've got an accompanying RAS map file that was created when we went into RAS Mapper and imported the terrain surface that we then cloned and then adjusted to get an existing and a project conditions terrain. And we also created and linked to a land cover layer to assign the roughness. So inside the geometry files, we made a computational mesh that we refined around Disneyland. And finally, we added a bridge and a culvert to the project geometry. In this part now, we'll be making the U01 file. Now the U stands for unsteady flow. The example I'm showing here has 4 different geometries and 3 flows, as you can see here. So in this case, you'd have the potential of having maybe 4 times 3 or 12 different plans if you wanted to run them all. I'm only showing 5 plans here. Those are 5 of the possible plans to demonstrate some of the comparisons that you might want to draw. Now, just to make sure the file management and schematics of HEC RAS are understood, sometimes you'll want to compare the same geometry with 2 different flow files like this one here. You'll need 2 different plan files to compare those. It's basically the same dirt with different water. Other times you might want to compare the same flow under 2 different geometries. So this is the same water with different dirt. You likewise need 2 different plans for that. Now, what we did in our last part was to set up an existing and a project conditions geometry linking to a single flow. Now, ours will be a big tsunami and a dam breach, not necessarily 1%, but this is the layout that we've got. 2 plans, 2 geometries, and 1 flow file. Now, I'm going to mention one warning that might not be immediately apparent if you're brand new to HEC RAS. So this might make more sense once we've actually put these elements into our model. But for this upfront warning in today's video, we're talking about boundary conditions, and those show up in 2 different places. The locations of the boundary conditions show up in the geometry, but the values associated with those same boundary conditions, those show up in the flow file. Now, where this can get complicated is when we start making changes to the boundary conditions. Say you wanted to delete a boundary condition location and change it to some other type. You can do that here in the geometry file, but the values that were previously stored in the flow file over here, they're tied to this geometry through this plan. But now it has nowhere to be stored. So if you save everything, they're gone. And if there's another plan that links to this geometry and a different flow file, well, likewise, it's gone. And if that links up to another one, well, you can see how this might get problematic. So you have to be careful. And sometimes when we're working with boundary conditions, it's best to just isolate the geometry and the flow so that you have them completely separate, like we show in this example right here. And in our case, we'll be using the same locations and values for all of our boundary conditions. So this is the condition that we'll be looking at. Now, before we dive back into HEC RAS, let's have a look at the files that are in our folders at this point. Now, the PRJ and the geometry files, the G01 and G02 files, they all ended up in this master directory when we created them. There are some accompanying HDF files as well. You can get more detail on that file format back in part 2. It looks like there's some automatic backups as well. The RAS map file goes here with its own backup, but geometry backups sometimes end up in this automatically created folder called backups. So having a look through the rest of our subfolders, I've got nothing right now in these first 2. I do have my land class Actually, I don't have that in there, which means that I didn't specify correctly the directory that I had here, the numbered one, and HEC RAS has created its own called land classification. Now, I like to keep things where I can find them again. I'll show you how to clean that up in a minute. I'm just going to copy that, hitting Control-C on the land class layers, and then coming back here and putting it in this one, which is the folder that I've designated. Now, I'm also recognizing that I used the term land use in the PDF file that I provided a link to. That's the old terminology. Land classification is the terminology that we're using now in HEC RAS. So I do think it's important to go back and clean things up before you get too far into things. If you do that periodically as you're building a model, like we're doing here, then you can just make sure that everything is where you want it. Now, I've broken my own rule about the log file here. I know we've got a log there. I haven't touched it yet, but it's best to keep that one current with each step. So under projection, there's still that single projection file that we're using. There are no reports or results yet, but under shape files, I've got these delineations, which I pulled in from HEC HMS, and then all of my terrains are here under the terrain folder, and the point, polygon, and polyline features are under this features folder that HEC RAS has created for us for any features that are directly created right within RAS Mapper. So I think that's all we've got for now. So let's go ahead and open HEC RAS up and clean a couple of things up before we start pulling in the water. So here's our main HEC RAS command window with the Disneyland project loaded. The last thing we did in part 3 was to add a bridge and a culvert to the geometry. But there's one thing I forgot to mention. Just like for the main description in the command window, never leave this description blank. Say something about the terrain that it's linked to, the roughness, the data sources, the grid size, or anything else that distinguishes this geometry from any others. So in our case, I'll call this the project conditions Disneyland berm, say something about the computational mesh we've used, where the terrain data sources came from, what roughness we're using, and the structures that we've put into it. So I'll go ahead and save that. I'm also just realizing that speaking of roughness and the bridge and the culvert, I'm realizing one more thing I forgot to do when we were pulling our bridge in was to go back to the cross sections and give them a roughness coefficient. Now, you don't need to do that with culverts, but for the bridge, we'll go ahead and add them here. In this bridge, what we need to do is go to the cross sections right here. And if you haven't assigned a Manning's N, it won't run. So if this is a concrete bridge, let's go ahead and just make this a 0.015. And I'm just going to make each of these beginning ones 0.015. It'll stay the same unless I horizontally vary this. And so for each of these ones, we'll give it a concrete roughness, assuming that it's all cleaned out along the bottom. So that way, I'll go ahead and zoom in on this so you can see what's going to happen here. We'll be able to let some water in through this bridge here. Maybe for this one here, also on this connection, let's do something simple to prevent any of the flow from coming up into it this way. So flow can go in this way, and if we want to keep it one way, then we can just go ahead and edit this culvert here. And on the culvert, instead of having no flap gate, let's allow flow to go out, which is that direction there, and no flow to go in. So I'm going to say no negative flow flaps, and we'll go ahead and save this geometry with those changes. Now, another thing I like to check before we proceed any further is to make sure that any land classification layers are correctly recognized. And these are like the check files that show what HEC RAS is actually doing. So I'm going to go back in and open up RAS Mapper, and under the geometry files, which we see here, we can go ahead and look at the project conditions one here. And if we expand this out, you can see the final N values right there. So we can see that that recognized the Manning's N of 0.035 out here, and it's 0.08 there. Now, like I mentioned, I don't like the ambiguity of having two different places for files. Either you take what HEC RAS gives you and use those folders, or you make your own. So let me just quickly go through the process of relinking things here if you wanted to clean things up. So I've copied the HDF files into my own directories there, into that O3 directory. And so I'm going to add this one then and remove the others. So under the map layers, I'll go ahead under my RAS layers and add an existing RAS classification layer right here. And so now I've got this one that I've just copied through here to channel. And so I've got this one in here, and I'm now going to go in and delete the previous one. I could go in and delete the source files as well, but just to show you what we're doing here, I'll remove that layer, and then I'll go back in here and delete it manually out of this land classification layer. In fact, I'm just going to delete this whole folder here so I can keep my straight. So now it's going to link back to that one because it had the same name. We could just check it again and make sure that we're referencing the right polygons. You can see it right there. The channel's in this one. I can right click on it and edit the land cover data table, and you can see that it's going to be 0.035 inside of that one there. And so now let's just make sure we save this and see if it'll recognize it after we come back in. So I'm going to exit out of this one, go ahead and save it here. And sometimes I like to just save the project, go out of HEC RAS altogether, and then when you come back in, sometimes that wakes it back up again. And when you're first opening up a project again, one thing I hadn't mentioned before is you can always just take this PRJ file and just drag it in here. The other way to get to it is under File. It'll be the last thing that you worked on here. You can just pull that drop down. So let's go back into RAS Mapper now, and we'll see if it has woken itself up. So here's RAS Mapper, and I'll maximize this here, and you can see then under the final geometry, if I go to final n values, again, when I hover around, this is my check file, 0.035 there, 0.08 everywhere else. Now, in reality, you'd probably have this broken down into a whole lot more classifications than this, but we're just showing you this to get a feel for how you might set this up. Now, I know we're supposed to be talking about flows today and we're still in the geometry, but no matter how long you've been modeling, you are likely to find some things along the way that could use some cleanup. And I think it's always easiest to do it incrementally instead of waiting until the very end when you might have hundreds of files and folders to try and sort through and get things cleaned up. So I'll go ahead and close out of RAS Mapper now, and we'll go back into the geometry. Now, all of the boundary conditions that we enter today are going to be the same in both geometries, the existing and the project one. But to avoid delineating things twice, I'm going to set all of the boundary conditions in this one, the project conditions geometry. And then once everything is done, I'm going to save that right over the top of the existing conditions geometry. So I'm going to take GO2 and save it over GO1. I will still have to delete out all of the structures from the copied existing conditions file, and then I'll have to relink it to the right terrain files. But I find that way of doing things a lot easier than trying to make sure I've got exactly the same boundary condition lines added to both geometries. And again, that's just my personal preference to keep things as consistent as possible, and then to make sure that I understand the results when I'm comparing plans to each other. Because that way, any changes that I see are only due to the things that I wanted to change, and not some obscure difference in how I delineated or imported a particular feature that was supposed to be the same between the two model runs. So we're going to choose some of the locations for our boundary conditions to put into the geometry file here. And I thought we'd start by just dealing with 5 of the most common ones. So we've got an external inflow, internal inflow, external stage or water surface elevation, external outflow, and precipitation. So applying these to a artist's rendition of a terrain surface here, we've got some external inflows that could come in from anywhere along the outside perimeter. These have to be positive into the system. The internal inflow, on the other hand, can either be in or out. You can bring flow into the system or suck flow out of it. The external outflow could be an energy gradient or a rating curve here along the edge. This location assumes that our perimeter stops right here along the dashed line. This can only bring flow out. But if we extended it all the way out to the coast and didn't have this one as the external boundary, then you could have an external stage boundary condition. And for this one, flow could go either way. We could also drop precipitation on it from the top, or even though we don't technically consider these boundary conditions in HEC RAS's terminology, you can lose water through the bottom as well, even though the model just removes it from what's coming in from the sky. So let's open up our geometry file and start assigning some locations to these boundary conditions. We'll cover more about these options once we open the flow file with the locations already in place. But like a lot of things in HEC RAS, you have some choices as far as where to do this. Now you can edit the geometry inside of RAS mapper. Some people prefer to do that. You won't see boundary conditions here in the geometry file until you start editing. We do have that italicized refinement regions there, but that's because we've deleted it. Once you start editing, then you'll see boundary condition lines right here. So you could enter those in. Now I'm going to come out of RAS mapper here and do it inside the geometry. That's just my own preference, but you may develop your own preference and try to do it in RAS mapper. So pulling up our geometry again, you'll use this button right here called BC lines, boundary condition lines. So I'm going to expand my geometry window here, and let's start with an external inflow. So I'm going to zoom in on the area here where we've got some inflow coming in on the Santa Ana River, which goes into this reservoir here, and then we've got a dam down below. And we'll go ahead and bring some internal inflow here, but to start with, let's grab an external inflow boundary condition that's going to represent what's coming in at this point here. Now, the orientations of the lines that we draw don't really matter for boundary conditions. So if I go out to the full plot, and if we picture this like a clock face looking down, it doesn't really matter whether you're delineating these in a clockwise fashion or anti-clockwise or counterclockwise fashion. Imagine if we clicked once for 1 o'clock and double-clicked to end it at 2 o'clock versus clicking on 2 o'clock and then double-clicking on 1 o'clock. When you're doing a boundary condition line, it's not really going to matter. That said, though, for consistency with everything else that we do in HEC RAS, my own preference is to stay in the habit of assigning orientation to be from left to right looking downstream. So if I'm going to bring inflow into this along a BC line, I'll click on that one right now. Let me just zoom in here a bit, and we'll just draw a cross section where we're essentially going to be perforating this impervious perimeter around the outside. Sometimes your draw tool will disappear and you have to click on this again. I'm going to delineate here from left to right looking downstream. So I'm going to start up here on this hill and move over to this one, double click out there. Again, I'm going anti-clockwise. So if I call this one Santa Ana River Inflow, that has now snapped to the nearest perpendicular cells that are adjacent to that line that I've just drawn. Now, in this case, like I said, when I bring in flow, it's going to come in positive no matter how I orient this line. But sometimes you'll see other lines in HEC RAS and you'll want to know which direction somebody drew it in. I know now which direction I drew this one in, but if you pick up somebody else's model, you might need to go into RAS mapper. Let me just save this real quick on geometry. And if you went into RAS mapper, now under this project, I should see a BC line. I don't see it yet. Sometimes you got to exit back out and remind it, wake it up a little bit and remind it that we have already drawn that BC line in there. So now when I look at the project here, you can now see this boundary condition line. So with anything that you might be wondering about in terms of the direction that something might have been drawn in, it's sometimes a good idea to just double click on it here in RAS mapper. Under visualization and information, you will see the directional arrows. And in that case, when I zoom in here, I see the arrow there, which indicates to me that this was drawn counterclockwise, anti-clockwise, 2 o'clock, then 1 o'clock, which means if I am in a boat facing downstream, left to right, looking downstream means flow is coming into this model. And again, you could flip that around, but if you started measuring flow inside of the perimeter itself and started drawing profile lines here, you could orient those either way, and it's just going to assign the positive and negative flow direction. Negative flow doesn't mean it's wrong, it just means it's in the opposite direction of the assumed positive flow direction. I picture these black and red lines being perforations in my perimeter. You can always click on this line here and plot the terrain profile underneath it. And so you can see now again in my chosen direction here, left to right looking downstream, you can see I've got this high mountain here on the left and it comes over to this lower hillside over here on the right. This is my cross section, but this is not necessarily the cross section that's going to be used by HEC RAS. It's pretty close to it, but if I actually wanted to see what was used there, I would need to actually just draw a profile line holding control down along that red and black perimeter line. So you can see that here. If I cut the terrain profile and plot, this is actually what it looks like. I'll show you the problem here, and if you're following along, you don't need to do this. But what if I took my BC line here? I'm going to just delete this for a second and draw another one, and I'm going to draw it way out here. So I'm going to come out this way, and I'm going to call this one Santa Ana river inflow. And when I do that, look, it's snapped pretty close to the same thing. If I click on this line now and I try to plot the terrain profile under the BC line, yeah, look at this. This is what it plots. HEC RAS isn't going to use any of this. Like I said, with the bread dough, it discards everything outside of this perimeter terrain-wise. You see this mountain here in the middle. That's not going to get used because it's going to go to the nearest perpendicular cells to this line. And this is actually what it's going to use. So here comes tip number one on our wish list is when you click on this line right here and try to plot the actual BC line, just plot the actual BC line because it doesn't use this line for anything or the terrain under this line for anything. Now I could delete this again, but just to get in the habit of being able to move things around, again, it's not like in RAS Mapper, different commands here. You have to edit and toggle on your move objects command here. I'm going to move this one back down to here, and I'm going to move this one back down to here, just so I'm clear on where this thing is going to be coming in. And then again, you have to toggle off, which I wish you could just escape to get out of that. And here now is your external inflow boundary condition. Now, one funny thing that HEC RAS does is to keep the label where the object was originally placed, even after you've moved it. So if you wanted to move this label here, you could just go back to edit, move objects, and we could put this closer to where it was. You could also rename this or do whatever you'd like with it. So if I accept my changes by toggling this back off again, just remember that these objects here, or these features, have to be either external or internal completely. They cannot cross the line. So we need to keep the lines fully outside or fully inside this perimeter edge. Next, we'll try some inside. But before we do that, one of the things that it's going to prompt you for when we get into the flow file, if you are going to use an external inflow line, it's going to ask you for the energy gradient. And if we wanted to approximate the energy gradient as the friction slope or the bed slope of the channel, you could do that fairly easily by holding Control down, and let's just move down this channel. And what we'll do is it'll cross this low flow channel occasionally. I'm going to try and keep about as much distance upstream as downstream so I can kind of go to the midpoint and see what the actual bed slope of this channel is. If I double click here then and see this cut profile from terrain and plot button, it's actually pretty consistent. I would technically want to connect these low spots to each other. You can see that right there. And so if I double click again on this line right here, again holding Control down, you'll actually see your dy over dx. That is your bed slope right there. It's about 0.4%, and that's pretty consistent. If I come around here and I'll just do a full plot. I wish you could actually do this in RAS Mapper. Maybe that's another tip for RAS Mapper for another day. But if I look at any of these rivers here, including say the LA River, some of these are highways, and so it's hard to tell which ones are which. But here's the LA River itself. So if I wanted to see what the slope of the LA River was, as long as I'm not messing around too much with the overall longitudinal flow path length by crisscrossing here, then when I double click at the end and try to connect these points with the profile line, I've crossed the low flow right there, and it should be a fairly consistent slope. So if you look right there in this reach of the LA River, right by Skid Row, you're at about 0.43, so about 0.4% as well in terms of your slope. So sometimes it's worth measuring those slopes just to get a feel for your energy gradients, because you will need those energy gradients in the end. And we start by estimating those as the bed slope of the channel, even though the energy gradient doesn't necessarily have to be exactly parallel to that. It's a good estimate to start out with. So now let's move into internal boundary conditions. I'll go ahead and try to draw some of these inside. Let's look at the dam itself here, and this is where we'll go downstream of the dam and just assume that a breach hydrograph is going to come in this way. So if I go to this same button, the BC line, left to right looking downstream, I will double click here, and what we're going to get then, dam breach, is the cells that it's going to connect to. Now, my preference, if I'm going to have a boundary condition line, would be to put a break line in here and line it up with that. Now, you could draw these any which way. A boundary condition line, if I delete this and try again on a couple of different ways of doing this, you can bring in boundary condition lines internally like this and bring them longitudinally along a section here as well. Dam channel, I'll call this one. And then you'll see Well, that's odd. It put it back in the same place. I'm going to delete this again and see what happened there. I'll try a BC line. Maybe I need to wake this up a little bit. If I draw this along this channel, it should connect to these spots right here, channel inflow. Okay, I guess that's a bit of a glitch. Let me try this again. I will file save this now, save the geometry with the boundary condition in here. I'm going to delete this boundary condition line, save it again without it. And now let me try this again. I will do a BC line and try to go along the channel this way. And as I do that, we should see it line up. Channel inflow internally. So I'm a little baffled. Let me delete this again. I'm going to delete my boundary condition here. And I will make sure that I've got no boundary conditions here. Sometimes if you want to find out what's in your model, you can go to Edit, Delete, and see, do you have any BC lines in here? And so all I have in here is my Santa Ana River inflow. That's my external boundary condition. So I'm not sure what's going on here. Maybe that's a little bit of a bug. I'm going to exit out of this. File, save. This is what we always do. Sometimes I exit completely out of HEC RAS, come back into the geometry. There is no boundary condition here. So hopefully when I draw this BC line, again, if I draw along the channel here, I should see a longitudinal section here, channel inflow. Let me try this again. It's coming back in the same spot. This is really odd. Okay, I'm going to get rid of this. File, save, get out of HEC RAS altogether. And let's see what happens when I come back into it, come back to Disneyland here, and we'll pull in the geometry and see if we can solve our problem this way. 90% of the time when we are teaching a class and somebody has a technical issue, closing down the software and coming back in will solve the problem. So that's always what we'd like to try first. And sure enough, getting out of HEC RAS and coming back in, this is what it is. So again, I could delete this out of the recording and pretend like everything goes perfectly when I run HEC RAS, but it doesn't, and this is what happens, and this is what you'll want to see. Now, this is not the preferred way. If you look in the documentation, which I'll link to below, the preferred way is to do a cross section and come across this way. You can bring it in this way. It's going to distribute the flow equally, unlike the external sections where flow will come in at the bottom of the section, no matter how many little sub-channels you might have. In this case, it's going to distribute it among all these points. Now, I have seen people do this as well. Let me see if I can do the same thing. I'm going to delete this a different way now, just to show you another way to delete things. We go in here and we go to our boundary condition lines. I'm going to take this channel inflow and delete it. And now one of the ways that I've sometimes seen people do this is to either snake the BC line around. Say you wanted to bring something in inside a pond or a reservoir. I'll exaggerate that a little bit here. You could come in and try to equally distribute the inflow among these kind of channels here. So this would be like a reservoir inflow or something like that. And again, it's going to do exactly the same thing. I'm going to draw a few of these just so I can do this all at once. I will draw another BC line showing another way that people do this is by spiraling around, come around this way, and we can kind of connect it to all of the cells here. And then each one gets an equal part of the flow that comes in. So I'll call this one spiral. And just so I can just do this one time, I'll go back in here and do our cross section, which is going to be our actual internal flow boundary condition where we'll bring the flow in. So this is internal dam breach inflow. So I'll bring that across that way. And so let's see what happens now when I save this, exit out of HEC RAS altogether. We should see which cells these ones connect to. So I will file save, exit, come back to HEC RAS into my model here. I'll open up the geometry. We should see a few of these. I'll delete the ones I'm not going to use, and then we'll proceed with the next boundary conditions. So let me just use my view command to zoom in, but you can see here the spiral, the cross section, and the snaking around, and how you might use internal boundary conditions. So I'm going to click on this one, delete that. Click on this one and delete that. So that was a little bit convoluted, but here are the cells that are going to get inflow from our breach hydrograph. Now we don't need to worry about the energy gradient here because even though you can enter that with the flow data, it won't actually get used as I understand things. The documentation does warn about some potential double routing if you don't use a cross section like we've done here. So be sure to have a look at that if you use any other alignments for your internal BC lines. I'll link to that below. Keep in mind there's no initial flow direction for flow that comes in here. So any inflow can just be bubbling up out of the ground. Depending on your flow rate, that could just be a trickle, or it could be this huge geyser just shooting out of the ground at each of these cells. So watch out. You can get some really funky results right around this area. So now let's zoom out. I'm going to go to the full plot here. We'll add an external outflow boundary condition. Even though this is the ocean here, I'm going to bring a tsunami in. I'll let it leave the system here. You would have a stage here, but just so we can show an outflow boundary condition as a normal depth energy gradient, I'll go ahead and just delineate one here. So we'll let flow out of our system here. I'll just call this outflow. You can see that links right up to it. We've now got the red and black dashed line that perforates our boundary and lets flow out. Now, typically you would let flow out along an actual flow path, maybe this river here, and so you could measure that energy gradient. If that's just a single channel, that might be easy enough to assign. If you're just doing an average over the whole thing, then you'd probably want to test some sensitivities, try a couple of different gradients, and just see how far that propagates out. In our case, we're just doing it to avoid some glass walling here, so that slope might not be all that crucial. But there are cases where the backwater effects from adjustments to the assigned slope here at the outflow boundary condition can propagate for miles and miles and even go all the way through to the other end of the model, depending how flat the rest of your terrain is. So definitely run some sensitivities on that. We'll talk about that in the next part to see how things change. Now for our external stage hydrograph, here's where we'll bring in our tsunami. You could enter a storm surge. You could enter from tidal records that you get from a buoy. You could just keep this as a constant value. That could be, sea level, it could be mean high or high tide, it could be any value that you pick. Just keep in mind, if this is tidal, flow can go both ways. So I'm going to call this one tsunami. That's where we'll bring that in. And so these cells will get a connection to a stage hydrograph. Now, if we want to let it rain on the entire thing, that's a precipitation boundary condition over the entire 2D area. We don't do anything at all with that in the geometry file. That'll get added as a boundary condition in the flow file. Now, another way that the geometry file can get hooked up with the flow file is with these things here called initial condition points, these IC points. Essentially, these just give us points where we can fill water in up to the terrain edge, right along any cell edge where it can hold water. Otherwise, it'll just keep spreading across the whole model. There is a full momentum episode covering IC points. Have a look at that if you're interested in more. I might hit more about these later on, but for now, let's save our geometry. We'll close it and we'll open up the flow file to start adding some values here. So there are 3 buttons you can use to enter flow data. It's these ones right here. Alternatively, you can get to that through the edit menu. So just like you can get to the geometry through edit geometric data, you can get to these 3 flow files by going edit and looking at these ones here. We've got steady flow, quasi-unsteady, and unsteady flow. This one's just for sediment. So let's talk briefly about steady versus unsteady flow. For a 1D model, you'd actually have a choice between the flat water surface here, it's a Q, that's the discharge, versus this one here, which is a Q as a function of time. That's the T in parentheses there, going up and down over this hill. For a 2D model, you wouldn't actually have a choice to use this one here, the steady flow. You would only be able to use unsteady. Now, we haven't really covered the difference between 1D and 2D in this series yet, why you might want to choose one versus the other. I thought we'd save that discussion for the very end, once we can see some of the 2D results. That way you can get a visual reference for some of the flow characteristics that might be missing in a 1D model. Now, if you already understand these concepts, you might want to skip ahead to the next chapter. For anyone looking for additional background on this, though, I'll highlight a few conceptual points. And these are covered a bit more extensively in a couple of videos that are excerpts from a Hydrology and Hydraulics Essentials course series. So here are a couple of videos that are available on the RAS Solution channel. In this first one here, we show some simplified cases where 1D and even Manning's equation give us essentially the same results as a 2D model. In this second one here, we cover some background about steady versus unsteady flow. There's a publication by the HEC team that does a good job covering this topic, or both of these topics, in writing. So that link to the PDF file should be provided down below. Now, like I said, you can't have steady flow in a 2D model, but you certainly can have constant flow. And there's a distinct difference. So constant doesn't necessarily mean the same thing as steady. Constant implies that it's held at that same rate for a particular amount of time. Steady, though, assumes that the time scale doesn't even exist, or rather the time frame is indefinite or it's infinite. So if you look at Manning's equation here, it will give you a correlation between the water level and the discharge. So essentially there's a single stage versus discharge rating curve relationship for any given geometry. But you don't see time anywhere in this equation. So where's time? If you turned this into a rating curve, you wouldn't see any looping or hysteresis in this one. You can't trace those differences over time. So maybe this slope, the energy gradient, changes over time. Maybe the roughness coefficient can change with time or with depth. But once we've agreed on a constant value for these elements, that relationship stays fixed. And so the assumption in this equation is that any flow that's in this cross-section that we're assessing with Manning's equation has been running at that rate forever and ever. So it's essentially an infinitely long time. So in the same way, if we put steady flow into a 1D model, it's as if that's been running at that rate forever and ever, and it'll just fill any storage volume instantaneously. So to nail down that concept, I think we need to recognize that the area under the curve of a hydrograph represents a volume of water. So it's a finite volume. I don't remember a whole lot from my university calculus, but one of the fundamentals that I do vaguely remember is that the derivative is the slope of a curve. And then the integral, if you integrate a curve, it gives you these slices that add up to the total volume of water, in this case, or the area under that curve. So in our case, if I go with an actual hydrograph here, the area under this curve here is a fixed volume of water. And it's the volume of water that passes through whatever cross-section line we've measured this here within this fixed 6-hour time window for the simulation. So for steady flow models, typically we'll just pick the peak and we'll make that constant, but we never assign a stopping point along this x-axis. So each of these rectangular grid elements, in this case, we've got 200 cubic meters per second on the vertical y-axis. And then on the x-axis here, we've got 3,600 seconds wide for this rectangle. So if we multiply those together, the seconds cancel out here, and we have got a volume inside of each of these rectangles of 720 megaliters of water. So if I count those up, maybe I've got about 15 or 20 of these rectangles here. That'll add up to about 10 gigaliters in total. So that 10 gigaliters of water ends up being the area under this unsteady curve. So how about the steady flow line here? Essentially, that flow just keeps right on going until after the universe ends. I mean, essentially, this is infinite. So what is the area under this curve? Well, if you added up an infinite number of these rectangles, essentially you'd have an infinite volume of water. So in my world here in Western Australia, where we assess a lot of mining pits, say you had a big river, but an even bigger mining pit. So here's a cross-section view of one, and here's a longitudinal profile view. Even though this is vertically exaggerated, that's actually to scale with some real pits that are next to or right inside of big rivers, even if the rivers don't look that big by comparison. So if I zoom in on that, you can see here looking into the page, if I had a cross-sectional view of this and this was a river, in this case this is a fairly large one, but a much larger mining pit, here's the situation we're trying to avoid. So my job sometimes is to try and figure out how big does this levee need to be, how high does it need to be to prevent the water in this river from overtopping into the mining pit. So let's say I did my job and contained all of the flow, except I got one little trickle of water over the top of this levee. And maybe it just happens for 1 second, just barely overtops. And let's call the total peak flow rate 1 cubic centimeter per second. So if that happened for 1 second, the total inflow volume would be 1 cubic centimeter. So my little syringe here, it would fit into the end of it. That obviously wouldn't even register in my model. That's if it was an unsteady flow model. Say it was steady flow, though, that 1 cubic centimeter of water would magically transform into gigaliters of water here in the pit because it would fill it instantly. So how long, if you made an unsteady model and made it constant, constant, how long would that 1 cubic centimeter per second take to entirely fill it? So we actually demonstrated that concept in this video that I referenced earlier, where I made the deliberate mistake of taking one of the no data values, a -9999 that's in your terrain file, and picked it up as an elevation. So 10,000 meters below sea level, we've got this big pit here. Now, if I ran this as 1D steady flow, even if it was only trickling in at 1 cubic centimeter per second, it instantly filled and spilled like it would do with my mining pit. So with 2D though, if I tried to apply that tiny little inflow, even if I let it continue constantly, it looks like on my model run times, I'd be waiting a year or more just for my model to run the 60,000 year time window that it would take to fill that void in reality. So of course that's an exaggerated case, but it does highlight some of the problems you might run into if there's a detention basin or any other storage in your model. Sometimes I think it's good to approximate things with a 1D steady flow model, or maybe even a constant flow 2D model, where you just hold the inflow at the peak flow rate. That usually gives you a pretty conservative set of results. And it might be tempting to use that, especially if it's 1D, because honestly, 1D steady flow models are a whole lot easier to stabilize than 1D unsteady models, which can get really tricky, especially when you start throwing in structures in the mix. So just be careful. Sometimes there would not have been enough water in the entire system, all in the catchment at all, to ever even fill that storage area that a steady flow model would just instantly fill. Another thing to watch out for, if I go back to one of these profile views, is that the flow that you get in this area here as it's coming down will have a zero effect downstream, because 1D steady flow models are computed from downstream to upstream. So you'll put something big in here and might be tempting to say, hey, look, there's no impact of this change that I made to the system downstream, when in reality there is a huge impact. So with that, let's open the Unsteady Flow Editor. We'll use button number 6 here instead of the drop-down option. When you open that up, you'll see a bunch of blanks here for the boundary conditions that we've put into the associated geometry here. You'll also have a blank for the Unsteady Flow file at the moment, this U01 file that we're creating. If you wanted to give it a name, which I recommend doing right off the bat, you go under File, Save. Save and Save As are exactly the same in the very beginning before we've named anything. By default, it'll put it into this master directory that we're working in. I'm going to just call this one Tsunami Breach. In general, you would call out the average recurrence interval, the annual exceedance probability, say something about the magnitude of this flow. In our case, we're just making up something hypothetical. And when I say OK now, we have this U01 file that's just been created. So just like the geometry, never leave this description field blank here, and always update it if you make a change. So I like to say something about the data source here. Where was it that you got your hydrology, for example? And then I also try to make sure that the hydrology study, the results that we're using, spreadsheets with the values that we're using, or anything else that's going to be listed here in this description is also copied into the hydrology subfolder for reference. So in our case, we've got a tsunami and we've got a dam breach. You'll see it's maroon there until I hit apply, and then I can save that again. Now I've saved a file here, but there's nothing in this file yet. So let's go in and start entering some of these numbers. We'll start with the first one that we entered, which is this inflow right here. So we've got a Santa Ana River inflow. And when I click on this, you'll see some things that are grayed out. Those are mostly for 1D models. And then you'll see a few options that we have here. So in this case, we're going to make it a time series flow hydrograph. So time being the critical term here, since we are in an unsteady flow file. Now for this demo, I'm going to bring all my flow in at the dam without any external inflow going in. So I'll save this one for later when we bring flow into the reservoir and maybe run it as a dam breach. So for now, I'm just going to enter zeros. So I'll put a 0 here on the top. I'm going to hold Control and the arrow down, put a 0 here in the end. I've got 99 hours of zeros if I hit interpolate missing flow here. I'm not quite sure how long I'm going to run this model, but I've gone out beyond the end. Because if you leave these blank and then your time simulation window ends up against these, it won't run. You have to put zeros in there. Now, I guess this is another one of my tips here, is that when you go to Precip, if you leave these blank, it'll still run and assume that they're 0. So why not for flow? Just if you have something blank here, just have it assume that it's 0. So it also asks you for an energy gradient here. Now this is where we need to remember the number that we extracted from the geometry. So remember, this is not a percent. I think we had about 0.4%. So I'm going to have 0.004. You don't see this menu here unless you expand it out. It will do a tailwater check on the anything that's downstream that's affecting the rating curve and basically submerging the rating curve at your boundary condition. You can have it check for that, and I usually just turn that on by default. So in our case, any water that we do bring in here will come in at this 0.004 energy gradient. So that's 4 meters per kilometer, 0.004 meters per meter. So why does this matter? Well, if we take an example here of a varying longitudinal slope and say we wanted to assign a boundary condition here as an external inflow, you would have a given Q, a discharge in cubic meters per second in our case, coming in at any given time step. Well, HEC RAS knows nothing about the terrain upstream of that external inflow boundary condition. So should it bring in the flow at this depth or at this depth? In our case here, the Q has stayed constant. We've got a V times A, that's velocity times cross-sectional area. If we used a unit width into the page, that area is going to correlate to the depth here. And so our velocity times area here stays constant, and here it's constant. This Q stays the same everywhere. So how does HEC RAS know what to use and what elevation to assign? Well, that's the energy gradient that you're going to specify. Once you've assigned that energy gradient, HEC RAS will then work out a rating curve. So going back to this schematic, you've got discharges coming in at the upstream end here, these external inflows. HEC RAS will take those discharges and turn them into elevations. Likewise, down here at the bottom, we've got an external stage here, and HEC RAS will take the stage and turn it into a discharge. In any case, HEC RAS needs to build a rating curve. So let's talk about rating curves for a second. If you had at any given point, if you're measuring the stage here, what HEC RAS is going to do then is build a rating curve. And that's essentially just a relationship between the stage and the discharge. So if you know the stage or the water surface elevation at any given time, you can draw the discharge from it. And likewise, you can take a discharge, come up here and draw the stage from it. So as the water comes up and back down again, at any given point, you've got a fixed relationship between stage and discharge. And then HEC RAS can just use those tables to do its computations. So we'll come back to rating curves in a second when we see them as options for outflows. But now let's get to some internal inflows. So coming back to our HEC RAS model, we now have an external inflow hydrograph, which you can see right here. The others are still blank. So let's click on the internal inflow. And in that case, when you have something that's inside of your 2D area, you only really have one choice. So you can see flow hydrograph right here is the one in black. The rest of them are grayed out. I guess this would be another one of my suggestions. It's not really intuitive when people first open up HEC RAS that you need to put something in here. And if there's only one that's going to go along with it anyway, it may as well just populate it and give you the option there, or give you a drop down here that says please select from what's available. In this case, you only have one thing available, and that's your inflow hydrograph. So in this one, let's see, if we started it out at 0 and we'll run say for 8 hours, and at the midpoint put 8,000 cubic meters per second. So I'll end this here at a 0 on this end. And like I said, if we decide to run it longer, I like to just put a 0 all the way at the very end here. And then I hit interpolate values. You can always plot out the data, and you can see your triangular hydrograph here. You can right click on this and zoom into the area that you're interested in. And here you can see we've got a triangular hydrograph coming in at 4 hours. One thing that's funny about it is until you've assigned your simulation window, look at this year here, 0999. So that's the default year. Now, like I mentioned, it's going to prompt here for an energy gradient slope. These aren't going to be used, as I understand. You can put in whatever you want. I don't think it would make a difference because there's no horizontal initial velocity or even any direction associated with this flow until it starts ponding up. So if I look at the actual location where this thing is coming in, you might have a case where when you first start bringing in flow, say this was really low here, you could have flow going in a reverse direction. It's got nowhere to go at the end. It initially starts heading this way. Then once it fills up, then it starts heading the other way. So the effective energy gradient can change over time. Now there's a video of that if you look up the Halloween special on the RAS Solution YouTube channel. One of the spooky things that we look out for here is that sometimes when you bring in an inflow, it's not the actual inflow that you're sending down the channel. So again, a steady flow or a constant flow at the peak flow rate would make it where there wouldn't be any difference. But if you're going to have an unsteady flow model like a 2D model has to be, sometimes when you bring it in, it might not be what you actually want to see. So in this case, for example, if you had a hydrograph coming in that peaked up at 1200 cubic meters per second, again, the volume of water that's coming in could be the same. That's the area under the curve here. If this area matches this area here and all you've got is attenuation, then sometimes what happens is that attenuation will occur where you've got your internal boundary condition, and what's actually moving downstream could be half the flow rate that you actually wanted to move downstream. So coming back to HEC RAS, let me get rid of RAS mapper here. Again, we've got these values here. It's a triangular hydrograph. One thing that would be handy, again, another tip, is if you could use these like in Excel. I like the interpolate button here, but sometimes you want to take a value and just drag it down. So that would be a handy thing to add. And another thing, sometimes you'll have thousands of values here. The number of ordinates that it asks you for, you start with 99 of them available. But sometimes if you wanted to go to a 5-minute interval and have a week's worth of time, you'd need a couple of thousand of these. So usually I go in at the very beginning and just set the number of ordinates to say, 2000. Otherwise you might get a bit of a glitch if you ended up with something lower here than the default of the 1 hour. Say you wanted to turn this into 1 minute or 1 second. You're only going to be able to get enough values, even with a couple thousand of them, that takes you a day or two into the simulation. So I think in the old days, maybe it took a lot of time or disk space to have all that. I think you may as well have it be more than 99 at least. So that's one more tip. Another thing I thought I'd mention as a tip would be if you could just summarize what's in here. Sometimes, you scroll down through thousands of these values to try to find where it is, or I'll take these and paste them into Excel to plot out where this is. You can see the plot data here, but sometimes you want to know what is that actual value. And if you could just sum this up here with a maximum, and maybe even a time to peak, you could even have the flow volume. Once this is tied to a simulation window, you could have the flow volume coming in. And those would just be handy summary details to have. So that's one more tip here. So I'll close this one out. Got 2 down, 2 to go. Let's go back here under outflow, double click on this one. You can see here the options that we've got available to us. Again, for my outflow, I wanted to choose the normal depth energy gradient. For this one, I'll make it a very mild one. I'll make it 0.001. It's coming out to the ocean here. This one's pretty generic. It does give you a couple of options here that we didn't used to have. So you can have a varying water surface elevation along that line, unlike a 1D model or similar to a 1D model where you would have a single water surface elevation along the entire line. So I'll say OK here, and that's all we need to do for this one. So now I'll click on the tsunami here. Again, we have the same options up here. I'm going to bring this one in as a stage hydrograph. So as I mentioned, this one could be like tidal gauge data. In this case, let's just bring in one big rise. Now, our berm, the Disneyland berm, was, I think, up at an elevation of about 50 meters above sea level, so we don't want to overtop that. So I'll bring that in at, say, 47. So I'll start it at an elevation of 2 meters. So that's already started a little bit high, so it inundates part of the coast and doesn't dry out some of the areas, the bathymetry that are below zero. And I'll bring it up to the elevation of 47. Let's make this one peak a little quicker. So it'll come up to 47. It'll come down to back to 2 here. And then I'm just going to keep it at a constant. Again, if I run this longer, interpolate the values here. If I put a 2 down on this end and interpolate them, then I can plot this out and you can see what it's going to do. It's going to go up to 47 and come back down to 2 here. So always good to check your plot to make sure you haven't got any typos in there. So I can see my interpolated values here, but again, back to that same tip. If we could just sum up maybe the high and the low, the maximum and minimum stage, then you wouldn't have to scroll through here to look for it. So moving on to precipitation, we're not going to add this right now, but I'll show you how to do it. If you use this button, this SA2D flow area button here, it'll give you the 2D areas to pick from. And if you bring this across and say, OK, now your Disneyland 2D flow area, in our case, has this blank boundary condition. Similar to some of these other ones, you only have one option anyway. So I wish there was just a toggle here that said yes or no, turn on precipitation. You don't have any other options. So when I click on this one and then click on precipitation, this is where you would enter your hyetograph. Now, we only had one area to pick from, but you could have geometries with multiple 2D areas or 1D, 0D storage areas all linked together with connections, or they could be independent areas that each get their own individual precipitation applied without even being connected. But once you've chosen a polygon instead of a polyline for a boundary condition, that's your only choice. So this is how we make a rain-on grid or a direct precipitation model. Now, there are some really cool things you can do with rainfall these days. You can specify rainfall stations at different locations. There are some other tabs here where you can add meteorological stations where you could have rainfall varying across your watershed, across the 2D area. So you can distribute rainfall spatially with different intensities. You can add gridded rainfall. You can pull in DSS files that have some of this data. I could paste in values here from HEC-HMS or from any other data source. But we need to keep track of whether we're pasting in rainfall excess only, where the infiltration and other losses have already been removed from the hyetograph that we're putting in here, or if this is the total rainfall and we're just going to use soils layers to specify spatially varying losses. So once HEC RAS has done all of its pre-processing, it only spends time computing water where there is water to compute. So if we went and added some rainfall in here, it's going to get every single cell in our model wet, and that can slow things down a bit. So we'll circle back to some rain on grid options later on with this model, but I'm just going to leave it as a dummy here. Maybe I'll just specify 0 precipitation in the beginning. Again, I'll put 0 at the end and just interpolate, so I know this has been zeroed out. Now, one interesting thing is this first value here. You could put in 1 billion millimeters of rainfall here, or whatever you want. It's not going to make a bit of a difference here. So my suggestion would be to just gray out this first value since it's not going to get used anyway. I'll just leave it at 0 for now. But similar to some of the other tips, if we could have a summary here, it could just tell you the total rainfall depth that you have during the event and maybe tie that into the simulation window once we've established that. So if you want to take a deeper dive into rain on grid modeling, I've got some videos here that I'll link to below. This link at hydroschool.org/frequency includes a spreadsheet where you can enter intensity, frequency, duration data for your area, and then generate a hypothetical synthetic rainfall pattern called the frequency storm. And that one gives you a pretty conservative estimate for inputting hyetograph values if you didn't have specified temporal patterns that you'd otherwise need to run. So we stepped through the differences between rainfall runoff models and rain on grid models in this video here that I'll also link to. There is definitely a lot of overlap these days, but in a classic rainfall runoff model, you would be representing the watershed or the catchment with a bunch of parameters that then affect how the rainfall is transformed into runoff, and then how that runoff is routed downstream when you start connecting the subbasins. So for rain on grid models, you're basically putting rainfall into each computational cell. So my little contraption here hasn't survived being packed into a suitcase over the years, so I'll have to put a video of it up here instead of showing it on my camera. If we are going to put precipitation on it, rather than bringing it in from the sides, we're now bringing it in from the top, and a rain on grid model can get different precipitation in every computational cell. Now it could be the same if I take this plate here and put it on the top of it and vary the tempo but not the slope of it. That is your temporal hyetograph, your temporal pattern. But what you could also do then with spatially varying rainfall is change the angle of attack. And then that storm could come through with a different hyetograph for every single one of the computational grid cells. Now I like this illustration here, which is from the Australian Rainfall and Runoff Guide. It shows geographic space in each of the flat layers. Now time is in the vertical direction. So if we were to rotate one of these cubes, then each column of the grid cell would represent a time series hyetograph. So in our model, even though we've zeroed it out for now, we've just assigned a single hyetograph to the whole 2D area, like the ones that you see here. So if you flip this one on its side, you'd have the precipitation boundary condition with each time increment being one of these layers. Now you could break it down further by the subbasin. We could look at the space time and average out all of the space or the cells for each time increment, or you could average each of the time increments for each space and just get a flat hyetograph. That might be pretty risky because you'd miss some of the rainfall bursts that would otherwise max out your peak flow. Now, for precipitation, it's especially important to know how long we need to run this for, because different critical durations might have different temporal patterns, and the infiltration losses would affect each pattern differently in terms of the resulting flow rates. So you always want to run it at least long enough for flow to get from the furthest point upstream from the source all the way down to the outlet. So sometimes what I do is I'll just put in a constant rainfall and then check the downstream outlet to see when we max out the discharge. And that will give you a feel for the time of concentration and the lag time. And so I'll do that sometimes before I ever even put in any real values. And at least it tells you what kind of time frames you'd be looking at when you're pulling in your rainfall data. So that should about do it for today's video. Let's just summarize a couple of tips for entering boundary conditions. Most of these tips have to get considered in the geometry before you ever even get to the flow file because they relate to the location and the orientation of the BC lines. So keep in mind we need a rating curve to be built into all of these boundary condition locations. So the more stable and uniform the flow is at that location, the better off you are. So as you're drawing your perimeter, you may already want to be thinking about how you're going to bring this in because you want it to be just like in a 1D model cross-section locations, you want it to be perpendicular to the flow. You want it to be fairly uniform, not just horizontally, but vertically as well. In some cases, it doesn't make a bit of difference to your area of interest because the changes related to the different orientations, the different energy gradients, or whatever other parameters you've got there only affect the cells in the immediate vicinity of the boundary. And so when we have a look at the results, we'll talk about what we're looking for when we're running sensitivities on some of the boundary conditions. So now that we've got our boundary condition values entered into the flow file, I like to save those just so you can get back to them. I mean, some of these have a lot of data in them. You might have made some changes to them. So I'll show what I do here. Typically, once I get all done with this, is I will go into the boundary conditions and just copy and paste them into Excel. So I'll pull in Excel here, and if I took this flow hydrograph, for instance, right here, I will copy this one, paste it here. Probably want to define the time window here. Likewise with the stage hydrograph, I've got some values here. I'll take that one, paste it in. I'll generally do this as a separate file, but just in the interest of time, I'll just browse to the hydrology subfolder and say this is my backup data, and that way I can get back to it anytime I want. Because remember, just like in the geometry file, I do not get an undo in the flow file if I mess something up and accidentally save over the top of it. Just like we'll see in the plan files as well and in the geometry files, we do not have an undo here. Again, that's one of my tips, is that I hope that they can get that added for all of the files in the future. So if we do a quick speed round of final tips here, this is probably my second top wish list item after depth varying roughness, and that would be in our precipitation file here for the hyetograph to allow negative precip values. Just like you can do negative inflow hydrographs and use that for some losses to pull some flow out of your system. If we could do that here for precipitation, then we could estimate transmission losses that only apply to cells that have water to actually remove rather than only pulling it out of the precip in the beginning. Another quick tip on the intervals here, and this might not apply to a lot of people, but in Australia for our PMP estimates, a lot of times you get 18-minute values here. So that might be something that could get added. In the meantime, all you do is break it down to a third of that value and then just repeat the 6-minute values instead. So that's a bit of a workaround. Now, if you are interested in using DSS files to translate back and forth between HEC HMS output and HEC RAS input, or sometimes you might get gauge data that's in a DSS format, I'm not going to cover that today, but I do recommend giving it a try yourself. And you can get an introduction to that topic from Martin Jacobs and the developers themselves right here in this webinar number 96. So remember, Australian Water School webinars are all numbered to make them easier to find. So thanks for joining us again today. That wraps up part 4. And in the next part, we will link everything up and run the flow over the geometry in an unsteady plan. So we'll see you next time for part 5. Bye-bye.